In the previous segment, we talked about the various kinds of problems generally which we will encounter under axial loading, and these are the set which we had discussed, and we will take up a one by one case and we will see how to tackle them. So, let us start with case 1 like this. So, here we have our condition like this. So, there is a bar of uniform cross section, okay, and then there are forces which are acting like this, maybe here, okay, and we also should be knowing the distances. Say here this is L1, here this is say L2, okay, and say here it's L3, and area of cross section is A, and maybe the Young's modulus is Z for the whole of the bar, okay, and we are supposed to find out the elongation, so delta. Suppose you find out how to find out the complete elongation, okay, because once you get the complete elongation, then you can divide by the whole length, that is L1 plus L2 plus L3, you will get the strain in a way, the full if you want to calculate. Okay. Now, what is the strategy for solving this? So, and then the first thing to think is this is not the canonical problem, and we have to break it into pieces in such a way that every piece will be a canonical problem, okay, the configuration. Okay. Now, so the strategy is whenever you see a discontinuity either in the force or area or material. So, in this case we are just discussing with the force. So, I will say that whenever you see a force discontinuity, you break that into pieces, okay. So, here there are how many discontinuities of forces. So, here as soon as we come to this location, we are seeing a concentrated force getting acted. Similarly, here as soon as we reach here, we are seeing this. That means, this is a segment which we will and similarly this is another segment which we can break into canonical configurations. So, let's give some names maybe. So, A, B, C and D. Then we will draw the free body diagram. So, as soon as you do that, so this can be done very dispassionately. So, the point is wherever you see a discontinuity of force, so that means as soon as a force is applied, you have to break the rod into pieces, okay, imaginary pieces, and then we will draw the free body diagram of individual segment. So, let us draw how many segments are there? 3, okay. So, then let us draw them. So, now one is this, okay, and this is A to B, and this side the force is F1. But then what to do about here the force which is coming? I mean, should we show the force which is acting here, or what should be shown in this free body diagram? See the thing, so this is the most important point in fact, okay. Then for this free body diagram, so FBD1, okay, I will say FBD of AB. So, for that what you should do is you can go to an arbitrary cross section, and so I am doing it here. You can go to an arbitrary cross section and see that what is the force which is coming there, okay. So, now this side F1 is coming. So, obviously this part is in equilibrium, right, it's not moving, everything is static. So, that means suppose this is some force say Q, okay. So, now that means Q minus F has to be 0, implies Q has to be equal to F. Now all this thing till the point you go to the section B, it's the force is F. So that means here you should apply F. Okay. Now let's go to the FBD of BC. Sorry, BC. Let's see what to do. Now the same thing. What we will do? You go and cut a section like this, and let's draw the free body diagram of this much portion. Okay. So here I am drawing like this. Okay. So this cross section say was alpha. So this was at alpha, and this is say at beta, and this is at beta. Okay. And then you just try to show the forces. So this side it was F1, and this was F4. Somewhere it was acting like this, F4, right? Now if this is F1 and F4, so now if a force here is acting like Q, so how do you write the equilibrium equation? Now Q minus F1 minus F4 is equal to 0, so implies Q is equal to F1 plus F4. Okay. So then now here you can draw the free body diagram like this. This is between, so here I should have shown the length, so this is L1. Here the length is L2, I think I have written there, L2, yeah. And yeah, so this area is same as this, slightly not drawn properly, but then what is the force which is acting on this side? Sorry. So here it is an F1 plus F2, F4, right? Sorry, F4, and this side it's F1 plus F4. So this full body or segment is under the action of a force F1 plus F4. In fact, you could have said that if you come from this side, in fact you could have said that it is F2 minus F3, and which will be in fact will be same. We can see that later. Okay. So this is how you should write, and then what to do about the other segment? Let's say FBD of that is CD, right? CD. CD. Now CD, if you come here a cross section, so you can say that it's F2, because see, I could have done like this. I could have added F1, F4 and F3, everything there, but that's in a way more complex. So on this side there is only one force, so what I'll do is I'll draw the free body diagram like this, which the length is maybe L3 there, and then the forces are, say, here and here it's F2, right, and here it's F2, and everywhere the area is A, material is E, area is A, material is E, area is A and material is E. Now all the 3 problems, now if you look at them, they are just like the canonical problems. and you know everything, how to calculate the delta 1 here, delta 2 here and delta 3 here. Okay. So let's give some numbers maybe, and then that will make more sense. So suppose this is say 100 Newton, say this is say F4 is say 20 Newton, okay, and this is say 30 Newton, and this is say 150 Newton, right? It has to be 150, isn't it? Because all these three things are on this side, I mean towards this left side, so this comes to 150, so to be in balance it has to be 150, okay. Now you see here, so this what in terms of values, okay, not in symbolic term, that is a bit confusing. Let's see in terms of numbers. Now this one, if you consider, this is under what? It is 100 Newton force and 100 Newton force, okay. And then this one, if we come here, what should be its value? F1 plus F4, so 120 Newton, right? So this is under 120 Newton of force, so this side also 120 Newton of force. And this is what? I was telling that we could have done the other way around, right? Means if we come from this side, if we instead of this, we could have written the FBD from the other side, okay. Now in that case, what we would have got? Q in this direction would have been F2, F3 minus F2, so in this direction, so that is 120 again, right? So F2 in this direction would have been, Q in this direction would have been 120 Newton, minus 120 because this side is plus 120, so this side would be minus 120. So it doesn't matter which side of the section, this imaginary section you keep, okay. And this again is what? This F2, so that means it's 150 Newton and it is 150 Newton, okay. Now, so that's the whole what do you call, way to analyze this, and then everything will, you know, so just see this, what it means is this segment is sometimes students get confused at this point, that this 100 Newton, why it is this 20 Newton is not acting on this. So once we go to the problem, solving some problems, you know what you can do is, just for a moment you convert them, this instead of 20 you just give it minus 20, so that the force is acting on this direction, then you can actually feel it also. In that case, what will happen is, let me do that. Suppose you have a case like this, okay, you have a case like this, and forces are acting, say, like the same thing we will put, this is 100 Newton, so here it was, say, this side 20 Newton. This, why I am doing this is, it will be more intuitive to think about what's happening actually. 30 Newton, and this is say 150 Newton, okay. Then you just imagine about these segments, okay. This is one segment, and similarly this is another segment, okay. So now think about them. So which portions are under tension and which portions are under compression? Now you see this, and then in this case, how the if you follow the same section method, you will get here what? It's 100 Newton here. So the FBD will be, you know, this side 100 and this side 100 for AB, and similarly for this, what you will get? You will get is if I come here, so 100 minus 20, so 80, fine, 80 Newton, and this side also 80 Newton. Now if, so I am cutting a section like this. Now if I keep from that side, again the same thing would have been there, right? So this will be, you know, what? Oh, just a minute, am I getting this 80? This cannot be 150, right? Because this, see, this should have been, this is not in equilibrium now. This should have been how much? This is coming to be 130, then this is 20, so 110, right? This is 110. Now it's in balance. So this side 130 and this side 130. Yeah. So then if you do it from this side, again 80, right? So that's what I was trying to see, and then I realized that I had done it wrong. So in this condition also, if you look from, if you keep this in the free body diagram, again this is 80 Newton you are coming. And if you come to a section like that, and if you draw the free body here, you will see 110 and 110, right? So that's how, so that means, see, though inside here it looks as if it is getting compressed, but the actual effect is of tension. Why? You just think about the whole, as a whole body, okay? If only this 100 and 100, suppose you start with this problem like this, say 100 and 100, okay? So this is one condition, then it will get some elongation and some stress, and then you apply say 20 and 20, and then you apply 10 and 10 in addition. So it will, you know, this addition of 20 here now cannot compensate for the whole of 100 Newtons effect. So still it is actually, you know, the effect of 100 has a part of that has been released because you are applying a compressive load, and it is coming to 80. Okay, so that's what is happening, and then but this this process of thinking about what's happening in effect is very easily done when you draw the free body diagrams by cutting a section at a particular location. So that's the easiest way to draw the free body diagram, and then once you draw that, you know how to apply the formula on individual segments. Okay, and then you can apply delta 1 plus delta 2 plus delta 3 and whatever. If it's in compressive state, so you will have to put a negative sign there, so that length will be reduced, so you can get the complete elongation. Okay, so I want to say something. Okay, in some cases, what happens if this full, by mistake I had written it there, right, say 150 in place of 110, because if I don't put 110 and if I write 150, what will happen? This whole body will start moving, right, because it is not in equilibrium. Then what will happen? It will have an acceleration as a whole body. If it is not bound by anything, only these are the forces which are existing, that means it will start moving, and because of that acceleration there will be a gradual loading that will come. It will be exactly like the case where we saw this, okay, because it will accelerate. It will be equivalent to a condition of uniform, being in an uniform acceleration field, gravitational field. So along with this, another stress, which is a continuously varying stress, will come onto that. Okay, we will see how to analyze that once we go to the case 3. Okay, but here for this first case, it should always be in equilibrium. Okay, I hope you have understood this. We will solve some problems, then you will realize that okay, how to break them and how to solve each individual to get the total solution. See you in the next segment.